Hello and thank you for tuning in to the second presentation of my thesis. In this presentation, I explain how to analyze the least loaded D, or in short, the LLD policy. More often than not, a queue is described by its number of jobs. However, for the LLD policy, it is more convenient to describe a queue using the amount of work it has left to complete all jobs currently present. One intuitive representation would be to see the queues as infinitely large glasses of water which have a leak at the bottom. When a new bottle arrives, we look at the glasses of water and empty the bottle into the glass which has the least amount of water left. It is clear that for this load balancing policy, all we really care about is the amount of water present in each of the glasses. Therefore, the way we distribute the work does not depend on the scheduling policy which is used. Therefore, the amount of water distribution, or in other words, the workload distribution of our queues, is independent of the scheduling policy that is used. However, the response time distribution is dependent in a non-trivial way on the used scheduling policy. Okay, having an intuitive idea of the dispatching policy, let us formalize the setting a bit. We have a dispatcher to which arrivals occur according to a Poisson process with parameter lambda times n. We have n equals to 5 queues which all complete their work at a constant rate equal to 1. The question we wish to answer is, what is the probability that a queue has W or more work at an arbitrary point in time? As time progresses, the amount of work in each of the queues decreases. Then an arrival occurs, which has some distribution for which we denote by lowercase g and capital G its density and cumulative distribution functions. This arriving job picks these servers at random. For simplicity, we set D equal to 2 throughout this presentation. Let us remove some of this notation to get a more clean view of the system. The dispatcher looks at the two selected servers and observes that queue number 4 will be able to start working on the incoming job first. Therefore, it assigns the job to the queue number 4. And the work is added to that queue. In practice, we may not know the amount of work present on the queues. In this case, the dispatcher can put a placeholder at each of the deselected servers. When these placeholders reach the head of the queue, they are consumed and the server fetches the associated job from the dispatcher. This stochastic system just goes on and on. Again, some time passes and another job arrives. The dispatcher selects two queues and will assign the job to the least loaded amongst the two selected ones. One could potentially describe this process as a Markov chain with a continuous state space of size r to the power n. Unfortunately, for this n-dimensional Markov chain, it is impossible to compute the stationary distribution for any reasonable value of n. Therefore, we will use the cavity queue methodology in order to analyze this load balancing method. We take a large cardboard box and place it in front of all queues. We then cut out of this box one cavity and call the queue which is behind this cavity the queue at the cavity, or simply the cavity queue. We observe that for this arrival, the job is assigned to one of the selected queues which we don't see. As we don't see these queues, we don't really care about what happens to this job. We are only interested in arrivals which select the queue at the cavity as a potential candidate to receive the job. We therefore define the potential arrival rate as the total arrival rate lambda times n multiplied by the probability that an arrival selects the cavity queue, which is d over n. So in total, we have a potential arrival rate equal to lambda times d. When a potential arrival occurs, we must decide to assign the incoming job to the cavity queue or another randomly selected invisible queue. To this end, we assume that all other queues are IID replicas of the cavity queue. Therefore, the second selected server has some work in its queue which has the same distribution as the amount of work at the cavity queue. When this amount of work is larger than the work at the cavity queue, we assign the incoming job to the cavity queue, and we again forget about this other selected queue. If the other selected queue would have had less work than the cavity queue, we would not have assigned the job to the cavity queue's work, and it would not have influenced its workload. We now use a level crossing argument in order to obtain the workload distribution of the cavity queue. To this end, we let W be an arbitrary positive value, and we note that the rate at which the work at the cavity queue increases above this value must equal the rate at which the cavity queue's work decreases below this value. That is, we must have that the downcrossing rate equals the upcrossing rate. For the downcrossing rate, we find that we have a downcrossing when the amount of work at the queue at the cavity is just a bit above W. Its load will decrease below W, and then we have a downcrossing. We can show that the downcrossing rate is equal to the density at the workload W. Which makes sense, right? As this quantity can be interpreted as the probability that the cavity queue has W work. For the upcrossing rate, we consider two separate cases. In the first case, we assume the cavity queue is empty when a potential arrival occurs. Zooming in on this case, we again consider two cases for the state of the second selected queue. In the first case, the other queue may have some work present, and we assign the incoming job to the cavity queue. And if the job size was greater than W, we have an upcrossing over the workload level W. In the second case, the second queue we select may be empty. In this case, we have a 50-50 chance to assign the incoming job to the cavity queue. And you would then have an upcrossing if the incoming job has a size which exceeds W. To summarize, we have for case 1 a probability of G bar of W that the job size exceeds W, a probability F of 0 that the cavity queue has no work left, and a probability of F bar W that the second queue that was selected has some work. Here we denote by a capital letter the cumulative distribution function, and if we write a bar over the letter, this should be interpreted as the complemented CDF. That is, F bar of W is 1 minus F of W. For the second case, we have a probability of G bar of W that the job size exceeds W. Then a 1 over 2, as we only have a 50% chance of assigning the incoming job to the cavity queue, and F of 0 squared, as both the cavity queue and the other selected queue must be empty. In the last case we consider, the cavity queue has some amount of work U which is smaller than W at the time of the potential arrival. Let us zoom in on this case. We again differentiate two situations. First, the second queue we selected may have more work than the queue at the cavity. In this case, we assign the job to the cavity queue, and we have an upcrossing in case the job size exceeds W minus U. In the second case, the second queue we selected has less work than the cavity queue, and the incoming job joins the other queue. We don't need to consider this case, as this will never lead to an upcrossing. Therefore, we may summarize this case as having a job size which exceeds W minus U, a cavity queue with exactly U work and a second queue with more than U work. This occurs with probability G bar of W minus U multiplied by F of U times F bar of U. Of course, we still need to integrate this value over all possible values for U. That is, we need to integrate from 0 to W. Given this derivation, we find that the downcrossing equals upcrossing rate can be written as F of W equals the potential arrival rate lambda times D multiplied by the probability of having an arrival of size W or larger to an empty cavity queue, while the second selected queue is non-empty, plus the probability of having an arrival of a size that exceeds W to an empty cavity queue, while the second selected queue is also empty, plus the probability of having an arrival of size W minus U to a cavity queue which has U work for some U which is smaller than W. Some basic calculus allows anyone to simplify the previous mentioned equation to an integral equation in which the only unknown quantity is F bar of W, the probability that the queue at the cavity has W or more work. This integral equation can easily be solved numerically, and we have answered our original question, because F bar of W is the probability that a queue has W or more work, and this can indeed be computed numerically. Now, in case job sizes are exponential with a mean equal to 1, we have some more analytical results. For example, we can compute the stationary workload distribution F bar W in closed form. We find the response time distribution in closed form. We also have a simple sum formula for the expected waiting time. And we also find a very simple upper and lower bound on the expected waiting time, and we can graphically illustrate the accuracy of these approximations. We observe that as D increases, these approximations become exact. With that, I would like to thank you for your time, and I'll see you in the next video.